Okay, so we've talked about enthalpy changes, and the change in enthalpy in many cases is really the change in heat of a chemical reaction or of a process. Okay, and we always define, as we've talked about, delta H, the change in enthalpy, as the final minus initial, or in the case of a reaction, the products minus the reactants. And so we've mentioned that for an endothermic reaction, heat is being absorbed by our system, and delta H is a positive value, and delta H is negative for an exothermic process or chemical reaction. Okay, now one thing when we are calculating enthalpy changes is one nice aspect of enthalpy is that it only depends on the initial and final states. That is, enthalpy is a state function. So if we wanted to measure the enthalpy change going from point A to point B, we could either do so directly, going from A to B, measuring the enthalpy of our products minus the enthalpy of our reactants, but sometimes a direct route is not possible, or at least not easy. And so what we can often do is to break it down into component steps. So we can maybe go to some intermediate state. We might call it C, for example. So we could go from A to C, and then from C to B. And the net enthalpy change would be the same if we go directly from A to B, or if we go from A to C and then from C to B. We would have the same net enthalpy change. And this is what we call Hess's law. Okay, and so Hess's law basically states this idea that the change in enthalpy for a process or reaction is the same whether or not that process takes place in a single step or in a series of steps. So let's take the example of the thermite reaction that we saw. Okay, the reaction is between ferric oxide, Fe2O3, which is a solid, which is mixed with aluminum powder to produce aluminum oxide and molten iron metal. Okay, now if we wanted to measure directly the enthalpy change for this reaction, we could do this using some type of a calorimeter, or we could simply calculate this enthalpy change based on two component reactions. Okay, one of these reactions is the conversion of ferric oxide to aluminum oxide and producing so the reaction of Fe2O3 with aluminum produce aluminum oxide and solid iron metal, and we can look up in a table, and the enthalpy change for this reaction is negative 851.5 kilojoules per mole. So for every 1 mole of ferric oxide that reacts, we release, that's what the negative sign means, we release 851.5 kilojoules. Now, in this process, the net process that we are interested in here we are generating liquid iron. Okay, and so we have a phase conversion between solid iron and liquid iron. That is, we are melting the iron metal, and this particular reaction is so energetic that the iron that gets produced is in the molten or liquid form. Okay, and so we could look up in a table that what is called the heat of fusion of iron is 13.8 kilojoules per mole. So for every 1 mole of iron metal that we melt, we absorb 13.8 kilojoules. Now, in doing a calculation like this, we first have to recognize that in our net equation, we are reacting 2 moles of aluminum and producing 2 moles of iron. So for every 1 mole of ferric oxide, we produce 2 moles of liquid iron metal. And we know from our relationships of enthalpy changes that these are extensive properties. That is, if it takes 13.8 kilojoules to melt 1 mole of iron, to melt 2 moles of iron, we simply multiply that value times 2, right? So if we had the reaction 2Fe solid going to form 2 moles of liquid iron, the delta H would simply be twice that, or 27.6 kilojoules. Okay, and so really what we can do using Hess's law is add up our component reactions. This reaction here plus this reaction here will add up to our net process, right? And what we can say is that the delta H, we're going to call this delta H total. We'll call this delta H1, and we'll call this delta H2. Okay, so the total enthalpy change for this process is simply the sum of the enthalpy changes for the component processes. So this equals delta H1 plus delta H2. Okay, so the total enthalpy change here will be delta H1 negative 851.5 kilojoules for 1 mole of ferric oxide reacting, plus this 27.6 kilojoules for our enthalpy change of melting 2 moles of iron. So we simply add those numbers in our calculator, and we find that the net enthalpy change is simply going to be a negative 823.9 kilojoules for the conversion of 1 mole of ferric oxide to 2 moles of liquid iron metal. Okay, so we can calculate the enthalpy change for a net process by breaking it into component subreactions and simply adding up the enthalpy changes for those different components.